In the last class, we have discussed about the classification of network elements. We have different classification: bilateral, unilateral, linear, non-linear, lumped and distributed parameters. Right. Active and passive elements. So likewise, we have discussed different classification, different elements classification. Now, let us we see the in the classification of passive elements. We have namely resistor, inductor, and capacitors. Now let us we concentrate on what is resistor, capacitor, and inductors. I think these are also you might have been studied earlier in your intermediate course. Anyhow, we will revise it once. Then we'll go to the next one. So materials in general have characteristic behavior of resisting the flow of electric charge. So every material will have a characteristic behavior of opposing the or resisting the flow of electric charge. And this physical property or ability to resist the charge or current, right, is known as resistance and is represented by a symbol R. The circuit element used to model the current resisting behavior of material is a resistor. So resistance or it is a property of a material which as a whole మనం ఎలా define చేసేది, it is a property of a material is a property of a material which opposes the flow of electric current, and the units for this one is ohms, and generally it is represented by a symbol like this. So a resistor is represented by a symbol like this, since it trying to oppose the flow of current. All right, flow of current I. So it is represented like a speed breaker. What we have, all right. So it is like a speed breaker to the current. Now let us look at this. Next one is inductor. An inductor consists of a coil conducting wire like this. So inductor is a coil. It is also a conducting wire having a coil length L and a cross-sectional area like this, and a core, and it is bounded on a core material with an n number of turns if it is bounded with n. So any conductor of electric current has inductive property and may be regarded as an inductor. So every conductor will have a inductive property when that conductor is wounded like this. It is wounded on a material or on a air core also. So, but in order to have enhance the inductive uh, effect, a practical inductor is usually formed into a cylindrical coil with many turns and conducting wire like this. So to have an effective inductance property, so what we do generally is we wound it on the a core like this, the wires. So then the applications are inductors find numerous applications in electronic and power systems. They are used in power supplies, transformers, radios, TVs, radar, and electric motors. So, so many ways of using these inductors. Then next term is inductance. All right, the property of a coil that opposes any change in the amount of current. Please look at this sentence carefully. Changing amount of current flowing through it is called inductance. So inductor is nothing but a wire. You say, all right. So and its property in inductance. So what is its property? The property of any coil, that is when a conductor is wounded. When a conductor is wounded like this. When a conductor is wounded like this, right? So when a current I is processed like this, and this I, if you are increasing this I through a variable resistance like this and a DC supply like this, right? If the current is increasing I, and this inductor will have a property of opposing the change in current. Change in current, it tries to, right, oppose the change in current flowing through it, and it is called as inductance. The property name మనం ఏమంటామంటే inductance అని అంటాం, right? So you all well know that uh, whenever a current is carried by a wire, it produces a flux. So now ఇక్కడ చూడండి ఈ coil, this coil, so this coil is carrying a current I. This coil is carrying a current I, and this produces a flux. So this produces a flux in this coil like this, right? Flux is nothing but what? Magnetic lines of force. This produces a flux. right? And due to this flux, so according to the Faraday's laws of electromagnetic induction, an EMF will be induced in that, and that induced EMF is represented like this here. So the flux linkage depends on the amount of current flowing through this one. This is due to Faraday's second law. So your Faraday has given two laws. One is Faraday's first law, another one is Faraday's second law. So what is Faraday's first law? States here it is: whenever a conductor carries a current, or whenever a conductor placed in a magnetic field, an EMF will be electromotive force. EMF means electromotive force. EMF. Electromotive force is induced in the conductor. So then that is first law. And the second law, what does the second law states here? It is whenever the amount of induced EMF is directly proportional to the flux linkages. So that is here. Look at that. Look at this diagram. The flux linkages is given by phi into I. Phi is proportional to psi. This is psi. We call it as where psi is equal to is flux linkages. What do you mean by flux linkages? Flux linkages is nothing but a number of turns multiplied by the total flux is the flux linkages. That is how much flux is linking with the coil. So the coil, if the coil is having n number of turns, then if the flux produced by the coil is phi, and therefore total flux linkages would be n into phi only. And this we call as psi. So and this is proportional to the current that is in the coil. So, and if you remove this proportionality constant, if you write, then we'll represent that phi is equal to L into I, where this L we call it as inductance. Where this L we call it as an inductance. Right. Now, as for this Faraday's second law, as I mentioned earlier, this flux linkages will produce an EMF. And the induced EMF is proportional to rate of change of flux linkages, and E is proportional to rate of change of flux linkages means d phi by dt. And if you remove this proportionality constant, what we will get is equal to E is equal to N into d phi by dt. And if you rewrite this equation like this, E is equal to d in by dt of N into phi. I will bring this N into the inside of this derivative. Right, N is an integer value. You can put here or you can put here. No, it makes no difference. Then what is N into phi? N into phi is psi. N into phi, this is equal to psi flux linkages, right? So therefore, this we can write it as E is equal to d psi by dt. Other equation you please look at this equation we have written here. Therefore, the induced EMF in a coil is given by E is equal to d psi by dt, and psi already we have derived it as psi as L into I. Right, the flux linkages is proportional to current I. Therefore, psi is equal to L into I, and therefore we can replace the psi with L into I. Then where L is a constant one, and then that you can bring it to the outside of this derivative. Then what we get is E is equal to L di by dt. Therefore, this is the voltage and current relation in a inductor. So this is the voltage and current relation in an inductor. So then what is the voltage current relation in an inductor? Inductor is the voltage current relation is given by E is equal to L di by dt. Energy stored in an inductor. Now to establish that, see here, according to the Lenz's law, the induced EMF should oppose the change in current flow through that coil, and the direction of induced voltage is given by like this. See here. So according to the Lenz's law, so we have a law called as Lenz's law. What does that Lenz's law states here? It is according to the Faraday's law, we know that an EMF will be electromotive force will be induced in the coil whenever a coil is linked with the flux. And the nature of the induced EMF in the coil will always have a tendency to oppose its cause. What is the cause of inducing EMF in the coil? Current. Therefore, due to the current it opposes. That is why, suppose if the current direction is I in the inductor is in this direction, then the induced EMF, this is induced EMF or induced voltage, also we can call it as induced EMF electromotive force, will be having a polarity plus here and minus here. if the current direction is. This is due to Lenz's law. That is, the induced EMF will always tries to oppose this. So the current oppose చేయాలంటే ఇది ప్లస్ మైనస్ ఉందంటే then this terminal will be at higher potential and this terminal will be at lower potential, and this higher potential will always having a tendency to oppose this I, right? Similarly, if the current is in this direction, suppose if the current is in this direction, then the polarity of the induced EMF would be like this, plus and minus, like this. So these two are the induced EMFs and this and that. Right, now let us come to the energy stored in the inductor. So energy stored in inductor is represented by energy stored. You might have been studied in physics, right? Is that there are two terms called as energy and power, right? Power we call it as work done. Power is nothing but work done, and whereas energy is called as work done per second. Work done per second is called as energy, right? That is why. So the total work done is given by the total work done per second per given interval of time. In a given interval of time, the total work done in a given interval of time is represented by integral P dt, where P is the power. Where P is the power, right? Therefore, and this power in an electric circuit, power is given by power in any element is given by voltage multiplied by its current. So that only we have a, in place of P we have substituted V into I, right? Then what is V here? V in an inductor, is, we already derived it as L di by dt. V in an inductor, induced voltage in inductor is given by L di by dt. Right, now you substitute this V in place here. Then what we'll get here, it is L di by dt into I dt. Then if I take the integral like this, L is since L is a constant, and then I will bring outside to the integral this L, and I will multiply 2 and divide with 2, nothing wrong in that, and I di 2I di by dt. So right, so this dt and this dt will cancel each other, then L by 2 integral 2I di. So what is the integral 2I will get? You will get it as integral 2I is equal to L by 2 I square, and this we can write it as 1 by 2 Li square. Therefore, energy stored in an inductor is given by half Li square. So that means an inductor will be able to store the energy when a current is flowing through the inductor, right? So the power in the inductor is given by V into I, and the energy stored in inductor is given by half Li square. This you might have been studied in intermediate physics also, right? Now let us just conclude it what we have discussed about the inductor. So the properties of inductor here it is. One is the induced. This is the induced voltage. Induced voltage in an inductor is given by V is equal to L di by dt. So the induced voltage across an inductor is 0 if the current through it is constant. That is, if I is constant. If I is constant, then what is di by dt? Di by dt derivative of a constant will become 0. Therefore, the voltage becomes 0. So voltage 0 indicates that if you take a wire like this, and if the potential voltage is 0, means what? It is a potential difference. Suppose if the voltage at this point is V1 and if the voltage at this point is V2, what is V? V is equal to V1 minus V2. And this is 0 indicates that these two terminals have the same potential. V1 is equal to V2. ఎప్పుడు 0 అవుతుంది? V1 when V1 is equal to V2 అయితేనే కదా. అంటే ఇవి రెండు కూడా సేమ్ పొటెన్షియల్ లో ఉంటేనే. అవి ఎప్పుడు సేమ్ పొటెన్షియల్ ఉంటాయి? when these two are short circuited, when there is nothing element in here. That is why see here the induced voltage across the inductor is 0, and if the current through it is constant, that means an inductor acts as short circuit to DC. Why DC we call it as? Why we DC we call it as direct current? That is a constant current. DC means a constant current. So for a constant current, the voltage becomes 0, and therefore your inductor acts as a short circuit. Then for small change in current within 0 time, if there is a small change in current with 0 time, that is d2 approximately 0 ite, then what will be the di by dt? Di by dt will be leads to infinite. So So it gives an infinite voltage, therefore voltage becomes infinity. Voltage becomes infinity if di by dt, when with zero time, if you try to increase the current, change the current, decrease or increase the current within zero time, then the voltage will be infinite voltage. So for small change in current within zero time gives an infinite voltage across the inductor, which is physically not feasible. It is not feasible generally, right? Then an inductor uh, in an inductor, the current cannot change abruptly. So therefore, the inductor property itself we already discussed that because of the derivative term involved in the voltage, then the current in the inductor always tries to oppose it, because the induced voltage always, according to the Lenz's law, it always tries to oppose the change in current. Therefore, the current in the inductor cannot change abruptly, since it does not allow the sudden change in current through it. It is called as current stiff element. So inductor ni kuda mana emanante current stiff element ani kuda maatladam. So an inductor behaves as an open circuit just after switching across the DC voltage, that we will discuss it later. The inductor can store finite amount of energy. మనం ఇందాక derivation లో చూసాం. E is equal to energy stored in inductor is equal to half Li square. That means L is a constant, and if I is also a constant current, if you flow it and it tries to store energy, a finite amount of energy, even if the voltage across the inductor is zero. So it stores the energy in the form of magnetic field. So the ideal detector does not dissipate the energy, and energy stored in it can be retrieved at a later time. So energy stored చేసుకుంటుంది, it cannot dissipate it, but that energy will be retrieved back to the circuit after some time. So therefore inductor takes power from the circuit when storing energy and delivers power to the circuit when returning previously stored energy. However, the physical inductor dissipates power due to internal stress. ఏదైనప్పటికీ కూడా energy, it does not consume any power, but because of ideal inductor does not consume the power, but whereas because of the wire, small internal resistance of the wire, and some power will be wasted in the or dissipated in the inductor.
Thank you one and all. We'll meet in the next session.